Okay guys, welcome back. We are going to start chapter 12 today, and we're going to start this on discussing inverse variation. So let's title them on the top. And first we're going to talk a little bit about it. What we've always graphed and we've done is we've worked with direct variation. That's where we had like y equals mx, and sometimes we put the plus b in there. It gave us a line. Technically a direct variation does not have that slope in there, but it has this relationship where y equals mx. Remember, m was your slope, and this was a graph of a line, or a linear graph. This is also what we call direct variation. That's what we've worked with all the time. Now we're going to talk about inverse variation. Inverse variation has a slightly different relationship between the coordinates. This is really common in a situation where you have, let's just say you have 5 people and it takes so many hours to do a job. Let's just say it takes 30 hours to do this particular job. Well, what we would do is, if we added more people, if we doubled the number of people, it kind of makes sense that 10 people, it would take half that time, so it'd take about 15 hours. If we doubled my people again, up to 20 different people to do the same job, it would take half of that, 7.5 hours. And this relationship where one's increasing, the other one's decreasing, is fairly typical in the workforce, and when they're talking about different leverages and different situations that take place mathematically. So the relationship between these is actually where you have y times x, or x times y, and it's going to equal some value. And we're going to call it k. We don't want to use m because slope was already used. K, and that's referred to as a constant. I know that's not spelled right. I'm going to spell it with a k for a reason. Constant of variation. Okay. And you notice on all of these, if we take 5 times 30, we get 150. If we take 10 times 15, we get 150. If we take 20 times 7.5, put that in parentheses because I don't want to confuse that decimal point as multiplication, I get 150. Then when we solve this for y, we of course divide both sides by 12. And we get y will equal 12.5. So we could figure out this value up here is 12.5. If we had 12 people, it would take about 12.5 hours to perform this job, whether it's doing inventory or manufacturing something. Doesn't really matter. I guess I should have wrote this the other way, but unfortunately I don't have an easy way to erase on this pen. Once I write it, it's there. So it goes against all my rules of using pencil for mathematics. One thing I do want to point out is this value here, the 150, that was my k value. So my constant of variation, and that's how these two items vary with ratio to each other, with proportion to each other, is 150. Now we're going to use that to solve other problems. One other thing I would like to take a look at real quickly before we get into the examples is a correlation between direct and inverse variation. So direct variation and inverse variation. If you're comparing points or coordinates, you have, remember, your x's and y's, points 1 and 2, but you could set up an equation real simply that does something like x1 over x of point 2 is equal to y1 over y2. And you could, of course, solve that by cross-multiplying using proportions. In inverse variation, it's a little bit different because you get x1 over x2 is equal to y2 over y1. Y sub 1, sorry. Those aren't exponents, those are subnotations. So it's a slightly different alignment of the values, and you notice how we just flipped over this fraction here from what we've been doing with direct variation. So we're going to use that in solving a few problems. And here we go. In example 1, oh, this paper never seems to end. Almost. Okay, for this problem we're going to talk about a traveling or driving time problem. And it's a word problem, sorry about that. It takes t time to travel a certain distance. Takes t hours or time travel a specified distance. And they give you something like the equation r times t equals 250. So r t equals 250. This is coming from, you recall back, where distance equals rate times time. So my specific distance in here is going to be the 250. And what we're looking at is the time it takes to travel that 250, I presume, miles that we're going to be looking at. And we'll set up a little chart. I'm just going to set this up as a horizontal table. We know that RT equals 250, so let's call this my rate, and let's call this my time in hours. And we know that if we have, let's just fill in some of the gaps here, 5, 10, 15, we don't necessarily have to have all the r values, we could do the other ones, but we know that we can solve for the t value by simply plugging in the r value. So To start with, we're going to go r times t equals 250, and r in this example is 5. So simply divide that, 250 divided by 5, and I get 250 divided by 5. We get a 50 down here. And then this one would be 10t equals 250. So if we divided 250 by 10, we get 25. And then this one would be 15t equals 250. So divide both sides by 15. 250 divided by 15. Calculator comes in handy. You get approximately 16.6 repeating. And you notice as my rate goes up, the faster I drive in this situation, the quicker I will get to the less time that I'm traveling. So you can fill this in for any value. You get up here for traveling at 50 miles per hour, you would simply be plugging in 50t equals 250. Constant variation is at 250, so divide both sides by 50 and you'll get 5 for your time, or your time in hours. Okay, so I'm moving on to another page here. This is 12.1, inverse variation continued. And here's what we're going to do. We're going to graph. They'll give you certain problems and they'll phrase it. Example 2, they'll say graph an inverse variation in which y varies inversely as x. Graph an inverse and when that tells you that, you can keep in mind that's where you have the x times y equals a constant. Inverse variation, and say y varies inversely. Y varies inversely as x. And y equals 15 when x equals 6. Don't know why some of my letters don't show up. Might have to find a different pen writing app here. So here's what I'm going to do. I'm simply going to do, we know that x times y equals my constant of variation. So I can easily come up with 6 times 15 will equal my k, which is 90. So k equals 90. And then we can go right back and write this into an equation. And if we were to graph it, we could use our calculator for that. So we're going to simply go back to x times y equals 90. That's my constant of variation. And of course, if we're graphing this, we want to solve it for y. So I'm going to divide both sides by x. And I now have my equation of y equals 90 divided by x. And that would be your equation that you graph. When you graph this on your calculator, you should go ahead and try it. You'll get an interesting little scenario because your window looks like this, and you're going to see a graph that does some funky stuff, and you're going to see a graph appear here, and you're going to see another graph appear here. We're going to talk a little bit more about why that is. Oh, this one didn't show up. There. Now we got it. We're going to talk a little bit more about why that is. Make sure your window is centered about a positive 10, negative 10 window. So this is what you should see in your calculator. Now I know a lot of you are saying I may not have that graphing calculator that you told me to get. I would try it on Desmos or try and get a graphing calculator. You might be able to call the school and get a graphing calculator if you're still needing one. So you will be using it quite a bit, and it's a good thing to have, and it's a good thing to know how it works and how the menus work. Okay, so for my next example here, I'm going to scroll it up a little bit. I already wrote it out. It says solve for x, and we're given that y varies inversely as x, and y equals 4 when x equals 7. So that gives me a x times y equals k. So I can determine from that first equation up there, that first statement of those coordinates, that 7 times 4 will equal my constant of variation. 7 times 4 is 28, so k equals 28. Now we have another scenario down here with some other points. It says find x when y equals 14. Well, you also know from that, because it'll follow true that x times y will equal k, so we know that x times 14 equals that same constant of variation. Remember, these k's are the same. So you can actually set these equal to each other, or when you solve this one, you got k equals 28. We can take this k value and just plug it in over here. So we get x times 14 equals 28. Divide both sides by 14, which is going to give me x equals 2. So when y is equal to 14, this one here has x equal to 2. Exciting, huh? Okay, for this next problem we're going to take a little example from physics and see how this applies to a quote-unquote real-world situation. So we're going to look at a balance beam here, and we're going to balance it on a point or a fulcrum, and we're going to put a weight on each side. Okay, we'll call this weight 1. We'll call this weight 2. So obviously, if this was exactly in the center and both of these were balanced, it wouldn't tilt to either side. So what the situation is we want to calculate, and we're going to have to put a divider in here and come up with a distance. So we're going to, since this is weight 1 on this side, we're going to call this distance 1, and over here we're going to call this distance 2. Now, if you move this fulcrum over, or if you slide that board with the weights on it, obviously it won't be balanced, but we could add one more weight to a shorter side. We had a shorter side of it. Sorry, these lines aren't drawn in. Gonna have to work on this. The equation that we can come up with here is weight 1 times distance 1 will equal weight 2 times distance 2. Okay, so for example, if we say we had an 8 kilogram weight, so let's just say that, let's see if I can scroll. I just realized here it wasn't recording as I did this last little equation. So I said the weight 1 times distance 1 equals weight 2 times distance 2, and I multiplied them out, so 8 times 1.8 equals d2 times 12. I multiplied the 8 times 1.8, I got 14.4 equals d12, divided by 12 on both sides, and I got my distance 2 equal to 1.2 meters. Which makes sense, because if that was a heavier weight, you would have to actually have it closer to the fulcrum to balance out that 8 kilogram weight. on the other side. So that's a simple example of inverse variation, and I will let you go with this assignment. And practice problems are on your paper, and don't forget to check your answers as you're going along. Make sure you're getting them correct. And this will be a good time to start hunting down a graphing calculator if you need to find one. Talk to you later.